Go today because we've had a bad track record. People I don't see here are Amanda, Chad, Hannah, Zach, Sally, who was here, Jerry, and Jaron. There's Jerry. Okay, so what we're going to do today is simply review for the final exam. So the exam will be covering chapters 1 through 17. It'll be Tuesday at 1 p.m. in this room. We have a shorter, it's a 2-hour exam period for the exam. I think everybody has seen the message. I've made that spreadsheet that's available to you on Moodle where you can just, assuming you don't have a Mac, because my Mac simply won't do it. It just stops working when I try to copy and paste into that spreadsheet. But if you have a PC, you can just take your grade report that you get from Moodle, paste it, make sure you're in the first column when you paste, into the raw data worksheet, and then the calculation worksheet gives you the summary of what your averages are in each area and what grades on the final exam would match final grades. It tells you which grades are unattainable and which ones you've already achieved. You can't go lower. So, right, that's a function that you used to be able to get with the projected final grade, but since we don't have it available, I think that really helps a student in planning. Okay, any questions about how to use that spreadsheet? And if you're like me and you have a Mac at home, send me an email and I'll just send you a personalized spreadsheet so you can get that information. No questions? Okay, I'm going to start my review from the beginning because that's the stuff that is least in your minds. The exam is cumulative, covering everything we've covered this semester. If you're wondering, second semester, the final exam is cumulative, but it's only over second semester. It's not cumulative over the whole year. So, starting with chapter 1, we had things that by now should feel so common as to be a waste of time to talk about, but just to review them. Scientific notation, just to make sure you know how to do that. Significant figures. There's still lots of points that I take off on things like Flip Fridays for people who aren't using significant figures right. So make sure you know your rules for addition, subtraction, multiplication, division with significant figures. And to put it real simply, multiplication, division, it's take the number of significant figures in each number. I assume you all remember the rules on determining what's significant. The smallest of those numbers is the number of significant figures in your answer. Addition and subtraction, you look at the last digit to the right that's significant for each number, and the one that is in the highest value position is your least significant digit, and we call that then the least significant digit for each number. The greatest of all of those is your least significant digit in the answer. So make sure you can do that. That was, maybe half the class had a problem with that on the first exam. Make sure you know the units, the SI units, for mass, kilograms. For time, seconds. For distance, meters. Those are the only base units we've used this year, I believe. Everything else has been a derived unit. So a Newton is kilogram meter per second squared. Right? So you have the derived units that are based on SI units. You need to be able to manipulate units. The prefixes you should have memorized. I don't want people to raise their hand and say, what is GPA? That is capital G, capital P, lowercase a. Not a grade point average. That you should know that G means giga. Or if you were a fan of Back to the Future, as obviously I was since I wore the double tie on Back to the Future Day, they said gigawatts because no one in their entire production knew how to pronounce giga. But you should know giga means 10 to the 9, right? You should have memorized the the list, what was it, from 10 to the minus 18 to 10 to the 18, I think it was. You should know all of those prefixes so I can ask you something about a femtometer. When I was in grad school, some of my friends were working on femtometer lasers. You should know what a femtometer is. Clue, that's smaller than a picometer, which is smaller than a nanometer, which is smaller than a micrometer, which is smaller than a meter. Okay, dimensional analysis, that's being able to analyze and make sure the units are correct in a value. And graphing. Now in lab, we spent a lot of time with graphing. But when I did looking at waves with graphing just last week, or was it this week? It was this week. I didn't get a lot of responses saying, well, if I have a position versus time graph, the slope is the speed. You should know those kinds of relations. And why we make graphs, because we can get so much information from them in a glance. They're very information dense. Oh, I forgot. I should put it in the presentation mode and hold out hope that it works. Nope. Something has gone amok. Much like in my office the other day, Michael, presentation mode, no longer working. Well, doesn't hurt us. What?
More than me, like it was my fault.
No. Coincidence. Okay, chapter 2, kinematics. Kinematics is studying motion. It's not studying why things move, it's just studying how they move. So we need to make sure we're comfortable with our kinematic variables. And so we have scalars, values that are just a number with units, or vectors, values that have a number, a unit, and a direction. So position, displacement. We have, position, I should have put distance here instead of position. Distance is, the words we use here can be annoying to me. But the example of I walk around the table once and come back to where I started, there is a distance that I travel, maybe 4 meters. But my displacement is 0 because displacement is just the vector going from the starting to ending locations. Speed versus velocity. Remember, these words I accidentally use interchangeably a lot. But what's the technical difference between speed and velocity? Right. Speed is a scalar, velocity has direction. Now, something I don't have listed here is the difference between instantaneous and average values. I think it stands to reason. Instantaneous must be at an instant, whereas average is over some span of time. But you need to be able to calculate, an average velocity, an average speed, an average acceleration. Notice there's only one word for acceleration, thankfully. Acceleration, the word can be used for either the vector or the scalar. You have to pay attention. What is acceleration? Okay, it's the rate of change in velocity. So rate of change means that it's the change in velocity divided by the time it took. And since velocity is a vector, an acceleration can involve either a change in direction or a change in speed. So, and of course I have time there because that's our last of the variables. Kinematic equations are the equations that relate those. So, now you have to see all of the stuff I do. The kinematic equations, you don't have to have them memorized, right? You're going to have the equations provided to you, but you have to be able to use them. You have to be able to determine when you're going to use one, how to choose them. Right? That's part of the problem-solving steps. So kinematic equations, the common ones are that equation, that's the one you use like 90% of the time. Why? Because it relates position, velocity, acceleration, and time. It relates all of the variables we had here. And it seems like most of the time we're trying to relate those. But then we had other ones like if we're only trying to relate the speed, acceleration, time, that's probably the one to use. Or if we're not relating time, then we would use that equation, which you see written in a number of different ways depending on what you're looking for. But those are the three common kinematic equations we use, and the lower two we use when we're missing a variable and don't care about that variable. Problem solving, we've gone through 4 tests. I'm pretty sure everybody's down with this. First thing when you're doing a problem is draw a figure. You want that figure to, of course, be the relevant figure, not just a random figure. So if you're doing a kinematic equations problem, something that's moving, you'd want your picture to not just say, if it says a ball is dropped, you don't want to just show a ball stationary. You want to have a ball and have something indicate where it starts and where it ends. The time it starts, the time it ends. Write down all of your variables with it. After you've done that, what do you do in a test solving situation? Yeah, write down the concepts involved. Make sure that you have clearly given your reasoning so I can look at that and say, yeah, person totally understands how they're going to solve this problem. Then identify the equations. Now, I know, in a pinch, you just look for variables. But you have to know what the variables mean. Like I said earlier, I have had a number of times where people choose an equation that's not even in the ballpark simply because it has variables that have the same symbol. But a variable can stand for a different thing in a different situation. You do have to know enough about the equations to know which variable is going to be important where. Okay, moving on. Chapter 3. Chapter 3, we started talking about two-dimensional kinematics. So it's just going from one-dimensional to two-dimensional. What's the big deal? When it gets down to it, there really isn't a big deal. Because motion is independent. That means if I take two perpendicular directions, I can take the motion in one of those perpendicular directions and treat it completely separately from the motion in the other perpendicular direction. The only thing the two have in common is time, of course, has to hold it together. You can't have a particle separate from itself. So independence of motion, you need to be able to break vectors into components if you're going to use independence of motion. So make sure that you're up to date on how to break a vector into its components using your trigonometric functions. Once again, you'll have the definitions of sine, cosine, and tangent provided for you, but you need to be able to use those to break a vector into its components or to find an angle based on the components. You need to know how to add vectors. So we have the graphical method. I have a vector like this, and I want to add it to a vector like this. What do I do? So I take one and put the end of it, or the beginning of it, at the end of the other one. And then my resultant, the sum when I add them up, goes from where I started to where I ended. So this here is showing, if this is A, B, and C, how do I indicate vectors? Arrow over it. So A vector, B vector, C vector. Then this is showing A vector plus B vector is equal to C vector. So you need to be able to do that. You need to be able to explain it or show it graphically. You also need to be able to break these into their components, how much in the x direction, how much in the y, and then add them by components. You add, as my high school teacher said, apples with apples. You add the x components separately from the y components. And that brings up this thing that is not in our textbook, unit vectors. Unit vectors are vectors that have a hat over them instead of an arrow. So if I put x with a hat over it, that means it's a vector, it has direction, but its magnitude is unity, which is Just going back to the Latin for 1. So unit vector has a magnitude of 1. It's there just to give you a direction. And so oftentimes you'll have x hat, y hat, z hat for your unit vectors. You might also see I hat, j hat, and k hat. And in more obscure situations, e sub I hat, e sub j hat, or e sub k hat. You will never see that last form, I don't think, in a general physics class. That usually comes in higher level classes by people who are a lot more esoteric in their thinking, or a lot more mathematical in their thinking. But you need to recognize a unit vector when you see it and be able to work with it. Okay, projectile motion is a special kind of motion. Projectile motion is when you study what happens when I take the ball and throw it to Reagan. Throwing it to Reagan because I have confidence that he'll catch it when I throw it off base. Okay, when I threw the ball, it had initially a velocity pointing what direction? It was pointing up at an angle like this. So it had a vertical component and a horizontal component. If we're treating the motion, I'm going to break it into 2 perpendicular directions. How do I decide what directions to use? Okay. Now she's gone to topics that now we can mix in. We didn't know them when we got here the first time. We just said, well, I want one direction to be parallel to the acceleration. And Tori went to, well, what causes the acceleration? The net external force. And so she said, making it parallel to the net external force. Same way as thing is saying, parallel to the acceleration. So choose your direction so you have acceleration only in one direction. Why? It makes your work easier. It's a simple reason. It's not because there's only one way to do it. It's because there's one way to do it easier than all the rest. So then if I talk about the motion in the vertical direction, it had an acceleration. What direction? Down. What magnitude? 9.8 meters per second squared. Remember, g is always a positive value. On this last test, there were a few people who put in g as minus 9.80 meters per second squared. G itself is a positive value. We use signs outside of that to indicate, what's going on in a problem. Okay, so vertical direction has a downward acceleration. It started going up, but what does acceleration do to motion? If it has an acceleration, the motion is changing. So since it was moving up and the acceleration was down, what happened to the upward velocity? It decreased until at its peak, the upward velocity was 0, and then it started coming back down. What was the acceleration at the very top of its arc? Still 9.8 meters per second squared down. If it stopped accelerating the vertical direction at the top of its motion, then it just would have stayed at that height for the rest of the flight. That would have been weird. Okay, now what about the horizontal motion? What was going on there? Assuming no air resistance. Go ahead, Mike. James.
Oh, it just stays constant.
Stays constant because no acceleration. That's why we chose so one direction had no acceleration, because that's trivial now. Okay, so you should be able to do those kinds of problems. Moving on to chapters 4 and 5. Look, I combined 2. So chapters 4 and 5 is where we talked about dynamics, the reason things move. So the dynamics, we had Newton's 3 laws. That's really what dynamics is about. It's about Newton's laws and forces. Forces, you better know force is anything that pushes or pulls. Is a force a vector or a scalar? It's a vector. Newton's second law, net force equals mass times acceleration. Is that a vector equation or a scalar equation? How do you write the difference between a vector equation and a scalar equation? So Newton's second law now when you look at this, one item doesn't have a vector sign over it. Why is that? Yeah, because mass is a scalar. It's written correctly. Mass is not a vector, but acceleration is. And in fact, I can't multiply vectors. Now, just for fun, we have an equation this equation is incorrect. It's not right. Why is it incorrect? Now, this is work, so it's from a future chapter from what we have here, but what is work? No, work is a scalar. Work is a force causing something to move. And if I have this tablet on my hand, am I doing any work on it right now? And of course, assume I'm not shaking. So no. Why am I not doing any work right now? Not moving. So now let's say I walk at a constant speed. Am I doing work now? Okay. It's still no work, even though I have a force and a delta x. The equation that's written right here would have said there's a work because there's a delta x and there's a force. What do I do to fix this equation so it correctly says no work if I go like this? Okay, there is an option. I can write this as equal to force parallel delta x. That is a correct equation. Or, what I was looking for, if I put vector signs over those two things, that changes the meaning of the dot. Instead of the dot meaning multiply, it now means multiply parallel parts. And of course, we had another equation like this. Now that we've gone through this, what is incorrect about this equation? Yeah, that means R times F. That's not correct. R times F is not the torque. If I have this weight in my hand and I hold it down here, I have a radius going from my pivot point, my shoulder, to the weight, and I have a force there. But what's the torque in this situation? It's 0. Why is it 0? There's no perpendicular force. That is a force perpendicular to the direction. Like this, there's a torque. Like this, there's not. So I have to put my vector signs. And if I put my vector signs, now the right side is correct. That time sign now means a cross product multiplying the perpendicular parts. You can figure that out because the little cross is perpendicular, right? They're right angles. That's why they chose it. They didn't put it vertical because that already has a meaning of plus. So, R cross F, what's the one thing that's still wrong? A cross product gives us a vector output. So I need to have those vector signs. If you don't have those vector signs, your equation is wrong. Because there's meaning to these things. They're not just random. I see so many times people who write the equations wrong, and I'm like, I failed. Okay. Newton's second law, net force is mass times acceleration. What's another way of writing net force? This sigma, which means sum of the forces. Now this equation, it's important that you realize that's the net force acting on an object you're interested in. So I could be interested in the body of the person in the problem. I could be interested in the ball in the problem. I could be interested in the scale in the problem. There's all kinds of things it could be. It's the sum of the forces on the object I'm interested in and the mass of that self-same object and the acceleration of that object. Right? This equation is specific to an object. And remember, since you're looking at all the forces on an object, internal forces don't matter. If I am looking at the forces acting on Anne, I really don't care about the force that's holding her neck to her or her head to her shoulders. That's internal to Anne. It's there and it's real. But it's not going to affect what happens to Anne if she pushes off of the table. And so I'm only looking at the external forces when I do this. If you look at the internal forces, they simply add to zero because of Newton's third law. Newton's third law says for every force there's an equal and opposite force. So if Ann pushes off the table, Newton's third law says the table pushes off of Ann exactly with the same force but opposite directions. Remember, I used examples of that like if you punch somebody, the force of your hand hitting their head is exactly the same as the force of their head hitting your hand. So if you punch somebody here where the head is really strong, you're probably going to do more damage to your hand because its ultimate strength is not as great as the head. Which reminds me, tonight there's another MMA fight with a guy I used to work out with here in Lincoln in his 11th professional fight, but 4th with UFC. So, not be watching because, of course, it's Friday night. But Saturday night, I'll be interested to see if he moves his record to 11-0 or gets that first loss. He never lost his amateur either. I just have to tell you, I took a physics student to his first ever amateur fight. He just pounded the dude until the round ended. Just kept throwing punches. The guy was just like this the whole time. He had to crawl to his corner. He couldn't walk to his corner. He couldn't get up. And they let it continue. It was crazy. He hurt the reason I'm talking about that is because he hurt his fist from punching the guy so hard so many times. Okay, so back to this. You need to be conversant with all of Newton's laws. Now, the first law, I don't put much emphasis on because the first law is the law of inertia. It's the law that says an object will continue in the same motion unless a net force acts on it. The second law incorporates that, so that's why I don't pay a lot of attention to it. If you know the second law, then you know the first law by default, because the second law tells you the relationship between force and acceleration, the change in motion. Okay, common forces. You need to identify forces. We have 4 fundamental forces. 2 of them are very short range. In general physics, we don't talk about those forces at all until we get to nuclear physics, because that's the only place where they're important. So we won't worry about the strong and weak forces as they're named, but we do have the electromagnetic force, which will be the focus of the first half of next semester, honestly, and the gravitational force. Those are the 2 forces that everything we deal with is relevant to. So gravity. Gravity, does that affect you? Yes. How? The only way that it fundamentally affects me is I'm pulled toward the center of the earth. Now, there's a gravitational force between me and all of you. It's pulling us all together. But it's so weak that I don't feel it. So we have that universal law of gravitation that says force of gravity is equal to G, mass 1, mass 2, over the separation between the centers of mass squared. I know that looks like radius, but it's the separation between the centers of mass squared. That force is really small between me and you because you have a small mass. My mass is small compared to the mass of the earth for sure. And so if you had the same mass as me, we would still have a negligible force. But it's because of the small masses we have. G is a small number, 6.67 times 10 to what, minus 11 Newton meters squared per kilogram squared. So you have to have reasonably big masses or an extremely small separation for this force to not be negligible. It is very important when you talk about planetary motion, very important when you talk about things like the formation and death of a star, because there's a lot of mass there. For us, it's just what's holding us to the earth. Everything else, all of the other forces that we feel are electromagnetic. The force that keeps me from going through the floor, what do we call it? The normal force. What direction does it point? Normal to the floor, which perpendicular is a 2-dimensional word that's equivalent to that idea. It comes directly out of the floor, so pointing up. But what causes normal force? When you get down to it, the molecules in the floor want to stay together. They don't want to be broken apart. And so to keep from being broken apart, they resist me trying to punch a hole through them. And it's actually the electromagnetic force that's holding the molecules together that's creating that normal force. What direction is the normal force if I push on this? It's coming directly out because it's normal to the surface. So if I have a slope, and if I put my pin on this, well, it's on a slope. Okay, not sliding. What direction is the normal force on the pin? Stylus. Normal to it, not vertical. Right? Not vertical, it's normal to the surface. So if you rotate the surface, the normal direction rotates as well. That I'm emphasizing because a lot of people fall into the trap of just thinking normal is vertical because a lot of times we're dealing with a horizontal surface. But if it's not horizontal, it's not. Okay, other force is tension. Tension is string, a force that is transmitted through the string that acts in the direction in which the string is leaving the object. Spring force. It's an elastic force that once again is caused by the electromagnetic forces that hold the molecules together in your string, or spring, excuse me. And so for springs we had an equation, the force in the spring is equal to minus K delta X. I put it there with the minus sign very explicitly because a spring has a restoring force. You stretch it, it wants to pull back. You compress it, it wants to push out back to where it started. That was important in our last lecture because that is the force relationship that allows you to have a simple harmonic oscillator. Because I went so quickly, I didn't talk about the importance of simple harmonic oscillators. Almost any force can be approximated as linear in a small range of motion. And so that means almost everything behaves as a simple harmonic oscillator if the oscillations are small. We saw that with the pendulum. If I have small oscillations, a pendulum is a simple harmonic oscillator. If the oscillations are bigger, it's not. Why is that important? Well, we have things like molecules that are held together with electromagnetic bonds. Those bonds within the range of stretching of a molecule can be treated just like a spring, force equal to minus K delta X. And so the motion of the molecules can be treated as simple harmonic oscillation. And that's why you can do things like your IR spectroscopy, where you're actually looking at energy being stored in vibration of bonds. You also have energy stored in other kinds of motion, but right now all we know about is vibration. Okay, then we had stress and strain. We need to know about compressive stresses. That's the forces going into the surface. So the force is anti-normal. Normal would be out. The force is in for compressive. Tensile, where the force is in the normal direction, pulling out. And shear, where the force is parallel to the surface. Stress is force divided by area. Strain is change in length over original length. So strain is the deformation. The stress is the force per area. Now we've just finished a whole lot of work talking about pressure. What's the difference in pressure and stress? Right. With stress, we have these specific types, the compressive, the tensile, and the shear. With pressure, it's the same in all directions. And pressure will just, if you have something like a fluid, the pressure will make a force that's always simply going directly into whatever it's touching. So if I have a liquid under pressure, on side walls it's pushing out. On the bottom wall it's pushing down. Okay. Oh, I skipped over something really important on that. Free body diagrams. You're going to need to draw free body diagrams on the exam. Anytime you're doing a problem that involves Newton's second law, free body diagram. If there is motion in more than one direction, you need to break your forces into components and then apply Newton's second law in each component direction. Okay, then we got to circular motion. So for circular motion, we started introducing things like angles. Make sure you know units of angles, things like radians. What are the units really for a radian? It's really no units. That's a way of saying it's an angle in the natural no units. Remember, an arc length S is just equal to the angle times the radius. For a complete circle, the arc length is 2 pi r. So that gives us, for a complete circle, 2 pi r is equal to whatever the angle for the circle is times r. Well, clearly, theta must be 2 pi radians for a complete circle. We also have the units of degrees, which is based on how much the Earth moves around the sun per day. It's essentially 1 degree is the angle of the Earth's motion around the sun each day. Not exactly right, because it would be 365.2422 degrees in a circle if they did it exactly right. Okay, angular velocity. Well, that was the symbol omega, not W, but omega. And omega is the change in angle over change in time, which it turns out is equal to the velocity tangential, that means the velocity going in the circular direction, divided by the radius. Angular acceleration, alpha, is the change in angular velocity over change in time, which means it's the tangential acceleration divided by radius. Now, don't get that tangential acceleration confused with the acceleration necessary to go in a circle. What do we call the acceleration necessary to go in a circle? The centripetal acceleration. And the centripetal acceleration, AC, is equal to v squared over r, or omega squared times r. And that acceleration is, as the word centripetal means, toward the center of the circle, which is perpendicular to the tangential direction. If I have something that's doing a circle, then don't let me forget to change. Okay, well, I'm changing it, so as long as I said don't let me. At this point, that was supposed to have been toward the center. That is my centripetal direction, and that is my tangential direction. Now I'm just going to put hats over them. What does it mean when I put a hat over it? It's a unit vector. I'm saying it's just a direction. No value here in terms of 379. It's just 1 for its magnitude. So those are directions. If I'm working a problem where a car is going in a circle, what directions should I choose for my x and y? The center of the circle, going toward the center of the circle, should be one of them. So you would want to set one toward the center and the other perpendicular to that. It doesn't matter if you're on a banked track or a flat track, you're going to want one of your coordinate directions toward the center because that is the direction of acceleration. And now it gets a little bit thoughtful. If you're going around a circle, the direction toward the center is changing, and the direction tangential is changing. That's okay. In physics, we can deal with our directions changing as long as we define them carefully. Okay, universal law of gravitation I did on the last one. Kepler's laws are applications of the universal law of gravitation combined with Newton's laws. All of those laws are actually Newton's. Kepler's laws predate Newton's laws by like 100 years. But they were based purely on observation. Kepler looked at the times for the orbits of the planets and said, I believe that all of the stars are orbiting the sun, all the planets are orbiting the sun in ellipses instead of circles. That's his first law. His second law says that the planets sweep out a constant area in time. That means if you take a line that goes from the sun to the planet, in 1 month's time, the area swept out by the line connecting the planet and the sun is always the same amount. The take-home, the thing I tell my astronomy students they have to remember is that means that a planet's going faster when it's closer to the sun, slower when it's farther from the sun. And then the third law relates the period, the time for one complete orbit, with the distance from the sun. And so that one we often write as the period squared is proportional to the semi-major axis, which I'm going to use R for, cubed. Once again, that's an application of Newton's laws and the universal law of gravitation that Newton came up with. Circular orbits are the kind that we usually focus on in physics because those ones we can do the physics on. We don't have to use any calculus. And circular orb, well, yeah, I'm going to move forward because we only have 9 minutes left and I am 6 of 17 here. I don't expect to review the stuff we've just done because it's fresh in your mind. Next came work and energy. Now I've talked about the work equation. Work is a force that makes something change its motion. And we in physics talk about mechanical energy a lot. Mechanical energy is energy that is useful to us. And so mechanical energy, kinetic energy. Something has energy because it's moving. What's energy? The ability to do work. So if I'm running, I have the ability to do work. I might be able to run through the wall, right? I run really fast and hit the wall. I might be able to pop through. I know I can't just come up to the wall and push the wall over. So I have the ability to do work because I was running. So what do we call that energy because of motion? Kinetic energy, since kinetic means in motion. So we have kinetic energy. Here we have two different types of kinetic energy. Translational. If I'm running, I have translational kinetic energy. Translation just means changing position. Rotation means going around in a loop. If I have a bob that I swing around my head, that bob, I can treat it as if it's just going around in a circle and has rotational kinetic energy. Now, if you want to be technical, you can calculate the kinetic energy of that bob by taking its speed, right? Speed is pretty easy to calculate here, and using the equation 1/2 mv squared. But if you have a complicated system, not just a single mass doing that, it's a lot easier to combine all the mass together and just calculate the kinetic energy of all of the rotating mass combined. And then we call it the rotational kinetic energy. Potential energy, any force that's going to give you back energy. You can do work on it. It'll give you back the energy. It'll do work back. We call it conservative. And conservative forces we define as having a potential energy. And so gravitational force is something that's going to give back energy, so we say gravitational force has a potential energy. Elastic, that is with a spring, has a potential energy. Gravitational potential energy was, different symbols, potential energy is equal to mgh. Elastic was potential energy is equal to 1/2 kx squared. We got that from making the graph of the force as you stretch it, and knowing that since work is force times the distance, that I just broke it up into a whole bunch of little boxes, which turned out I found the area under that triangle. Area of triangle is 1/2 base times height. The base was x, the height was kx, 1/2 kx squared. Electromagnetic and chemical, we'll learn about the electromagnetic later. You got to take a chemistry class to learn about the chemical one. Nuclear, we'll learn about that when we get to nuclear physics the end of next semester. Other types of energy, one we've been studying recently, thermal energy. What is thermal energy? Now that we've gone through this, we can answer. Yeah, this is something that on the last test there were a lot of people that missed. Okay, thermal energy is actually microscopic kinetic energy. It's the motion of particles on a microscopic scale. If you look at this table, it appears stationary. But the molecules in the table are actually vibrating. And the internal energy, the thermal energy and internal energy are identical in meaning. The internal energy or thermal energy is the sum of all of the kinetic energies, all of those molecules in the table moving back and forth. Now, what people missed on the test, the question, there were two related questions, but the primary one was, what is heat? And heat, a couple people had really nice, they clearly memorized correctly what heat is. It's the, to quote, because somebody actually did the exact quote, the spontaneous transfer of energy from a hot area to a cold area. It's a transfer of energy. Heat is a transfer of energy. It's not internal energy. It's not thermal energy. It's a transfer process that is caused by temperature difference without any motion. Motion, that's work. But if it's just the heat transferring, then it's going to be, well, heat. See, I said heat transferring. That's kind of... So now we know what thermal energy is. We can talk about it. Vibrational energy, when we talk about a simple harmonic oscillator, it has energy that's going back and forth between potential and kinetic. We combine those and call it vibrational energy. Acoustic, that means sound. When I speak, there are particles that come out of my mouth. They have kinetic energy. They collide with other ones, and they pass on that energy. And so I have a wave of energy. That's an acoustic wave. It's acoustic energy. Of course, seismic is earthquake. The work energy relationship is very important. Work net is equal to change in kinetic energy. It's really what defines this whole thing. Energy is the ability to do work, and this is the relationship. And then we define potential energy as change in potential energy is equal to minus the work conservative. And so if I take the work net and say, well, I have a conservative and a non-conservative part, this becomes work non-conservative is equal to change in kinetic energy plus change in potential energy. So when we did work energy problems, which we did a lot of, there'll certainly be work energy problem, at least one on the test. When you draw your figure, instead of forces on your figure, what you want to do is identify the potential energy at the starting and ending points, and the kinetic energy at the starting and ending points, and any non-conservative work that there may have been in between. And then you use this relation right here. So they're pretty simple and straightforward when you do those work energy relations. Draw your figure, identify the kinetic and potential energies at your starting and ending locations, and any non-conservative work, put them into that equation. And I see I had some duplication, well, between this and another. I have 2 minutes left. Chapter 8, impulse and momentum. Momentum, mass times velocity. Is that a scalar or vector? It's a vector because velocity was a vector. So momentum has direction. We had a question on the exam about finding the pressure when I have a bunch of oxygen molecules hitting the wall. Those oxygen molecules hit the wall and it said they had an elastic collision. What does it mean if it's elastic? It means that your kinetic energy was conserved. You didn't lose any kinetic energy. So the molecules have an elastic collision, which means they're not losing any kinetic energy. It means the velocity stays the same in magnitude. So they bounce off. It told us they came with 600 meters or 400 meters per second that direction. So they come back 400 meters per second this direction. What was the change in velocity for those particles? It's going to be 800 meters per second. There were a number of people who put 400, forgetting that it was bouncing back. Its velocity changed from one direction to the other direction. So the change in velocity was 800 meters per second. And then we had this occurring for 6 seconds. And we had the mass of the particle. So we take momentum is mass times velocity. Change in momentum is the mass times the change in velocity divided by the time. That gives us the net force because that's Newton's second law. Net force is equal to change in momentum divided by change in time. So using Newton's second law, you're able to find the net force, and then finally pressure is the net force over the area, and you were done. So that was an example of using this Chapter 8 material about collisions in a thermodynamics problem to help us understand. And we had gone through the whole derivation of the kinetic theory of gases. Make sure you can do one-dimension collision problems, whether it's elastic or inelastic. Inelastic, they stick together. That's the easier one to do because your condition is V1 final is equal to V2 final. If it's elastic, you have kinetic energy initials, kinetic energy final. Takes a lot more work. Okay, we are out of time, so that's where the review ends. I will post all of these slides, though, on our